Okay, the last law we need to talk about is the ideal gas law. Essentially, this law is a combination of all of them. It combines the three Boyle-Charles Gay-Lussac laws, essentially your combined gas law, with Avogadro's law. So, the ideal gas law is PV equals nRT, where P is your pressure in atmospheres. So for this one, it will matter. You do need to have specific units for your pressure and volume. It's going to be your volume in liters. N stands for moles. And then R is a number that is required to make this relationship work. It's not as direct a relationship as what we've dealt with before, or the numbers you could just plug them in as is. So every time we use this equation, we need to include this constant. Okay. The units on here are important because that's what determines why pressure has to be in atmospheres, why volume has to be in liters, okay, why you need to use moles instead of grams. And then, like we've always had to do before, you need your temperature in Kelvin. Okay. So, ideal gas law works best if you have a pressure of less than 1 atmosphere. Doesn't mean we won't use it for other situations. It just means that in a lab setting, if you were to use this and you had higher pressures or other things that make your gases less than ideal, then you'll end up with more error in your lab. So you've already written this down, but just to reiterate the fact that ideal gases are gases that technically do not exist. Okay? So while gases can fit some of these rules, there are others that they never truly can, though we can change conditions to try to make them as close to ideal as possible. Okay? So some of the hardest things for real gases to actually obtain, they are tiny, so it's easy for them to be far apart relative to their size. But the collisions between the gas particles being elastic is nearly impossible to make happen. Inherently, there's some friction, some energy lost every time that these particles collide, so they are not truly elastic. But we can make it so that they collide less and the amount of energy they're losing is small, and for certain situation, we can ignore it. There's also gas particles need to be in constant rapid motion. Okay, this is one reason why we always want to run things at a high temperature, because that maintains this. Okay. Another thing that is nearly impossible to make happen is having there be no forces of attraction between the particles. Okay, again, we can reduce this significantly by using small nonpolar molecules, but that is something that is very hard to maintain. And then the last component was the average kinetic energy of the gas particles being just dependent on temperature, not on size, but unfortunately, kinetic energy is in some ways related to mass, and since the different gas particles have different masses, it's best if you use a pure gas. That way, at least in this situation, everything is the same. So, keep in mind, real gases do have attractions between their molecules. Real gases do have volume, and real gases do not have elastic collisions, meaning that they do lose energy when they collide. So, again, what we can do to make a gas act as if it is an ideal gas is make sure that we are running things at high temperatures, low pressures, and using small non-polar gas molecules. Your best examples here are going to be your diatomic elements and your noble gases. Okay. Alright, so gases at low temperature and high pressure, or large polar gas molecules, are going to be ones that behave very not ideally. Okay, so molecules like water, which is polar, or pretty much anything with an OH group. And again, it doesn't mean we can't use these relationships with these types of gases. It just means that inherently we will have more error if we use them. So, using the ideal gas law, we have PV equals nRT. So what pressure is exerted by 0.00 306 moles of gas in a 25.9 milliliter container at 9 degrees Celsius. So a couple of conversions. I guess what we have is we have N, we have V, and we have T. Oops. Okay, so now let's start plugging. We also have our constant, R equals 0.0820821 liter atmospheres mole Kelvin. Those units on that constant are there for a reason. So now let's start plugging in numbers. So we don't know P. We do know volume, but it's in milliliters, so we have to convert that to liters. So 25.9 milliliters, 1,000 milliliters to 1 liter. That's 0.0259 liters. And then our moles we can plug in as is because it's already in moles. If, say, you had a mass, what would you have to do? Hopefully you are saying convert to moles. Our R constant, 0.0821 liter atmospheres mole Kelvin, and 9 degrees Celsius needs to become Kelvin at 282 Kelvin. Okay. Now, to get P by itself, we need to move the numbers on the same side with it. So we've got 0.0259 liters. If we divide, that cancels that out. So we're also going to divide on this side. And if you write out your units, you can use those as a way to double check your work. We have moles, and then moles underneath a fraction here, so those cancel. We have Kelvin on top and underneath a fraction, so those cancel. Then we have liters on top and liters under the fraction, so those cancel, leaving us with atmospheres, which is the unit for pressure. So if you go and actually calculate this out, you get 2.3 something something something, and it's high enough to make you round, so you get 2.74 atmospheres. Okay, so the reasoning behind keeping 3 sig figs is we have 3 here, 3 there, and when we add to make Kelvin, 282 has 3. Okay, so the ideal gas law is one, it can get you out of having to adjust for STP to use the 22.4 liters. There's one nice thing about it, because it has moles built in, it does that for you. So we have you react magnesium and hydrochloric acid at 22 degrees Celsius and 760 millimeters of mercury. If you produced 6.65 milliliters of gas, what mass of hydrochloric acid did you start with? So this is that same equation that came from our molar volume lab. We have magnesium plus hydrochloric acid makes hydrogen gas, which is diatomic, plus MgCl, and then to cancel out charges, there's a -1 and a +2, so I need 2 chlorines, which means to balance, I need a big 2 in front of HCl. Okay, so first thing what we need to do stoichiometry is we need to get ourselves to moles. The ideal gas law will take care of that for you. So we're going to have, let's see, PV equals nRT. We know pressure, temperature, volume, and R, of course. So we're going to find moles from this. So I'm going to do 760 millimeters of mercury into atmospheres, which would be 760 divided by 760 times 1, which will give me, with sig figs, 1.0. Okay, because I have 2 sig figs here, so I'm going to put that 0.0 in there so that I know I still have 2 sig figs. So we have 1.0 atmospheres times 65 milliliters. Again, got to convert that. Divide by 1,000, multiply by 1 liter, and that gets you a 0.065 liters, and that's going to be equal to moles that we don't know times 0.0821 Oh, I'm writing this wrong. Liter, atmospheres, mole, Kelvin, times 22 degrees Celsius plus 273 is going to make 295 Kelvin. Okay, so now I want to get my unknown on by itself. So that means I'm going to divide out what's multiplied to it. 0.0821 liter atmospheres mole Kelvin, and the 295 Kelvin, which means those have to go in over here. I keep doing that. Yeah, that 0 in front of the 8 is a very important 0 because it definitely messes up your numbers if you leave that off. So, to go through and see what units are canceling, I have Kelvin in the bottom of the unit fraction here, so which makes this Kelvin higher than it. I also have liters that are higher and atmospheres that are higher, so what's left is moles, which is good because that's what I want to solve for. So, if I calculate this out, I get a number like 0.0268 and a bunch of decimals are going on past it. The key is here, that number, I don't want to round yet because I'm still multiplying and dividing after this when I go to my stoichiometry. But essentially, this step right here was my convert to mole step. Because I now know that I have 0.00268 ... moles of hydrogen gas. Which means, since I'm in moles, I'm ready for my molar ratio. Molar ratio from my equation is going to be 1 mole of hydrogen on the bottom and 2 moles hydrochloric acid on the top, because there's a 2 there. And then we have 1 mole hydrochloric acid on the top, and then since I want to find mass, I need to know my molar mass, which is going to be 36.461 grams of hydrochloric acid. And that gives me 0.19 and a bunch of numbers following it, except I need to round up. So to get the correct sig figs, I'd write 0.20 so that I still have sig figs, and that's grams of hydrochloric acid. Okay, so make sure you do the online quiz, and I'll see you in class.